Swayam Prabha. Digital India. Educated India.
In the last class, we had learnt how to calculate the volume required for the propellant or the volume flow rate, and then using the burn time, the overall volume of the tank, right. And we had also come up with the equation for the mass of the pressurant, and we said it is equal to okay. This was the equation we had come up with, and this is valid under cases wherein the time of operation is small, right. If the time of operation is large, and also if you have cryogenic propellants, right, then if the temperature of the pressurant gas and that of the propellant are very different, then there will be heat transfer between the gas and the propellant, and that needs to be accounted for, because if you look at it, the propellant will evaporate, right, and because of its own vapors you might not require so much of the pressurant gas, right. So we need to take that into account in cases where the time of operation is large, or if you have cryogenic propellant. So let us look at it now. For long burn time, if it is cryogenic, then there is heat transfer between the propellant and the pressurant gas, okay. Now, how do we take that into account? One is we should calculate based on the H value, right. This is a convective heat transfer, so we have to calculate the convective heat transfer coefficient and then calculate the overall heat transfer, right. So you will get something like Q is equal to okay, where H is the heat transfer coefficient, right. This is for a case wherein mostly there is a very little flow rate of the pressurant gas, right. A is the contact area between pressurant and propellant. Okay. Then T is the operation time, and TE is propellant temperature, and TU is pressure and temperature at the end of expansion. Now please remember that we are putting the pressurant at a very high pressure in the gas bottle, right. It is around 350 bar, but in the tank the pressure comes down to something like 30 to 40 bar. So there is an expansion that is happening between 350 and 30, and because of which the temperature will also drop. So this temperature accounts for that. Okay. And TE is the propellant temperature. Now if you are using liquid hydrogen or liquid oxygen, we need to be especially careful because TE can be very low. If it is liquid hydrogen, it is of the order of 20 Kelvin, and if it is liquid oxygen, it is of the order of 90 Kelvin. So very low temperatures, and because of which the propellant is going to evaporate, right, and therefore we need to find how much is it that it has evaporated and suitably account for it in terms of the pressurant. So this is one part of the calculation. We have calculated what is the heat flux, or what is the heat, not heat flux, this is heat transferred from the pressurant gas to the propellant, right. Now the same heat that is absorbed by the propellant causes it to evaporate, right. The propellant absorbs this heat and evaporates. So if we have to calculate that, so the same Q will be transferred to the propellant and it will lead to its evaporation. Remember the propellant is a liquid, right. So it has to change its temperature from its temperature to its boiling point temperature, and then there is a constant heat of vaporization, and then it becomes a vapor, and then it has to go towards the temperature of the pressurant, right. So there are three components. Okay. So this is the liquid phase, L corresponds to liquid. So this is the PV is vaporization temperature, then TE is the temperature of the propellant, HV is the heat of vaporization, then TU is the temperature of the pressurant. Okay. this CPL and CPV are specific heats of liquid and vapor. And mv is the mass of vapor. Okay. So, we get if we know all this, we can calculate this quantity, right. So, we will know the mass of vapor. Now, if we know the mass of vapor, then through the ideal gas relation we can calculate the volume of vapor. Vv is equal to okay. So, we know the volume of vapor that is going to be evaporated, and based on this value, this is the volume of the tank. So, the volume of the pressurant that is required is Vt minus Vv, right. Part of the vapor is already given by the propellant itself. So, you need a smaller volume of the pressurant gas. So, that is right, and based on this we can calculate again the mass of the pressurant required from the same relationship. So, this will be mg would be okay. So, in this case, if you notice, because of the vaporization of the propellant itself, the mass of the pressurant required is reduced. Is this a good thing or a bad thing? Yes, we might be reducing some amount of pressurant gas requirement, but overall you are losing some propellant that cannot be pushed into the combustion chamber to burn it. So, in a sense you are going to get a reduced ISP, right. This, if you can prevent it from happening, it will be a better situation, right. Now, this is the heat that is transferred from the vapor or the pressurant gas to the propellant. So, we have used this to calculate the mass of vapor. We know the mass of pressurant required, right. So, we can calculate what is the temperature at the end of this using the following relationship. So, that is we can calculate the mean temperature of the pressurant that is entering. Now, if we look at the tank volume, let us say this is the tank with either fuel or oxidizer stored. There is pressurant here, okay. Now, we accounted for heat transfer from this surface to the pressurant, right, fine. There is also a possibility that heat might be transferred from the walls to the propellant, and therefore, there will be extra vaporization that will happen, right, and depending on the temperature of the surroundings, it might also happen the other way in some cases, wherein if the temperature of the liquid is higher than the ambient temperature, you could have reverse transfer. So, we have to account for that also, and also the case wherein the pressurant is transferring heat to the wall, right. Both these things need to be accounted for, and they can be accounted for in a similar fashion as we have done here. Only thing is the Q that we had here, right, Q will be equal to Q plus or minus Q wall 1, okay. That will be equal to mass of vapor into everything there, okay. So, Q wall 1 is between wall and propellant, and similarly if we are looking at what happens to the pressurant, then Q is equal to mg Cpg we have included plus or minus to account for the situation when wall is at a higher temperature and the propellant is at a lower temperature, and also the other case where the propellant is at a higher temperature and the wall is at a lower temperature. Similarly here too, and Q wall 2 is nothing but okay. So, we have learnt how to calculate the volume and the mass of the pressurant required. This is in terms of what is happening in the tank, right. So, if you look at what are the processes that are happening on the pressurant side, okay, we will look at it now and we will see how things go there. So, after all this we know how much of mass of pressurant to be delivered and at what temperature and pressure, right. So, fine. Now, if you look at what is happening on the pressurant side, you have, let us say, a helium tank, right, and you have a valve here and then a regulator. This is the and here it goes to the propellant tank, right. Now, if you look at what is happening inside this gas bottle, because you are drawing out gases, it was at some pressure, very high pressure initially at around 350 bar. Now, you have started to take out mass from this. What happens to the pressure inside? Pressure drops. If pressure drops, what happens to temperature? Drops. And as a consequence, again, because this is a constant volume process, right, you will at the end of the expansion have a lot of cold gas that is of no use, right. You understand the point that if you have gases, you will have some amount of gases at the end of the pressurization process that is cooling down very rapidly because it is undergoing expansion, and therefore its pressure also drops because of that, right. So, it's not going to be useful because of this. Let us look at how the pressure drops. Pressure drops through either, if there is no heat transfer from the wall of the pressurant bottle to the ambient. If there is very little heat transfer, then it is an isentropic process, or otherwise it would be a polytropic process. And this process is an isentropic or a polytropic process. So, you will have okay. If it is isentropic, then it will be gamma n is equal to gamma, otherwise n will be lower than gamma. Okay. Now, this means that we have to carry more pressure and gas in order to account for this drop in temperature and therefore drop in the pressure, right. The one way to mitigate it would be to heat it up in some sense. If we could heat it up, then or if we could maintain the temperature, if let us say we maintain the tank at in an isothermal condition, right, then this problem would not be so large, but otherwise if we can heat it, it will be better. So, let us look at that, but before we go there, we have done all the calculation to find out what is the stored gas requirement. Let us write that down. So, the stored gas requirement is equal to propellant tank requirement plus residual gas in the pressurant tank plus residual gases in okay. We had calculated this part as mg, right, fine. This is what we discussed right now. You will have to have some gas in the pressurant tank, that will not be useful, and this is, if you look at the gas pipeline, just like we had propellant trapped in coolant tubes and other tubing, you will have some gas that will be trapped in the pipeline, right. So, this accounts for that portion. Okay. Now, let us look at what are all the possible designs to mitigate this problem of coolant gas temperature falling and therefore you requiring to carry a lot more pressurant. One of the designs to overcome this is to have in the helium tank itself a heating This is a heat exchanger. Okay. If you have a heat exchanger here, as the helium cools down, if you supply heat to it, then the temperature won't drop so much, and therefore you will have a lot more of useful pressure. Okay, this is one way of doing it, but the trouble with this kind of a design is, if you look at it, you are designing a gas bottle which can withstand very, very high pressures, right. Just doing that itself is a not such an easy job. To design something that is leak proof and that stays like that for some time is not easy. Now you want to have something wherein you will have either a gas or a liquid recirculate or go around that. It is not going to be very easy. Okay. Then you have, you can keep it running, and you can keep the temperature such that you can look to maintain the same temperature as you had in the beginning, right. You are going to have some temperature. As soon as you start drawing, if you start heating it up, the temperature will fall because of expansion, and because of heating you can increase it at a rate such that you maintain the same temperature, or even if you increase the temperature, it is also better. Only thing is, you need to be careful that your tank is designed in such a way to withstand that kind of pressure. The other design that people have come up with is in this design we do not tamper with the tank itself, but okay. In this design you are not really looking at tampering with the helium tank itself, but using the concept of heating the gas in another way, right. Here you could even contemplate using a part of the exhaust, part of the combustion chamber gases could be bled to have this heat exchanger, right. There are various other designs that are possible, and some of these are discussed in this book by Hussel and Hang. You can take a look at it. There is one more design that people have only talked about but hardly ever used. One of the problems with all this design, if you look at it, the density of the gases, even if you compress it to something like 350 bar, what is the density going to be? If you are assuming helium, helium or if you take nitrogen, nitrogen is the same as air, density at ambient conditions of nitrogen and air very similar. So if you are increasing the pressure to 350 bar, it is like 350 times the density of air, is around 350 kg per meter cube, right. This density is very low, so you need a large volume, and therefore the weight of the pressure in tank goes up, because if you have a large volume, remember the design of the tank, it is PD by 2T. So the thickness of the wall goes up, and therefore your weight will go up. The other way to approach this problem is to use a solid propellant, right. Let us say we were to use a solid propellant then and generate gases which can then pressurize the liquid, right. If you were to do that, if you look at the density calculations, density of solid propellants is of the order of 1600 to 1800, right. It is already a 4-fold increase there, but there is a problem there, that is one of temperature. If you look at the exhaust of solid propellant, it will be of very high temperature, then such a thing might not be useful here. So we need to look at ways to cool the exhaust, and one of the methods to do that is to use something known as oxalic acid. Now this oxalic acid is nothing but H2C2O4, and its chemical structure is like this, molecular structure is like this. Okay. Now the good thing about oxalic acid is it decomposes upon heating, right. So if you heat this, it is going to decompose to water, carbon monoxide and carbon dioxide. Okay. So in a sense, if you pass the exhaust gas from a solid propellant over a bed of oxalic acid, then you can bring down the temperatures. Pressure is the only thing that you are interested in, right. If you look at it, pressure is the only thing that you are interested in, and if you can bring down the temperatures, that is a very good thing to do. Okay. So the final temperatures after an oxalic acid bed is something like 200 degrees centigrade is possible. So let us say you have a solid propellant only a conversion nozzle is good enough here, because you do not want too much of a pressure drop. You are not interested in velocity here, you are only interested in pressure. And then if you have a chamber which has this oxalic acid pellets, Then the exhaust of this can be connected to the or let me do that also. Let us say you have this at the head end of the tank, right. Then what you need is something like a diaphragm So, here you could have the you need this diaphragm simply because the temperatures are also still quite large. Even if you are looking at achieving something like 200 degrees centigrade, as I talked about at the end of at this point, right, it is still probably a little higher. So, if you have a diaphragm, you could reduce the temperature across the diaphragm, and also you do not want the pressure and gases to be interacting directly with the liquid, because then it could directly short circuit and go out of the tank also, right. Then if it pressurizes on this side of the diaphragm, then this can expel out the liquid. People have compared all these designs and looked at how much of a saving in terms of weight and other things can you make by using such systems, and we will see that in a table here. If you have helium with no heating, right, then the stored gas is helium, and helium at gas produced is also helium, there is another scale of temperature called the Rankine scale of temperature. So, this is in that unit. Then the weight is 182%, then volume is 183%. Now, if we have heating, right, in the helium gas bottle itself, helium is the stored gas and the gas produced is again helium at a higher temperature now. And therefore, the volume and the system weight reduces essentially because you can now have a smaller tank, and therefore the thickness of the tank will also reduce. So, you can look at it as this being the reference one and all this being comparisons with the reference one. Then the last thing that we discussed, that is solid propellant gas generator with subliming coolant like oxalic acid. Oxalic acid, then you will have CO2, H2O, CO, all this at around 1000 Rankine, and this could lead to a phenomenal saving in weight as well as volume. Okay. You look at these numbers, these are very small compared to this, right. But the challenge, as I said here, is you are looking at having here very high temperatures, and at the end of it you should have lower temperatures here, right, and you should be able to have a controlled burning. This kind of a system, if you have a solid propellant, is not amenable to having start and stop, because you cannot start and stop a solid motor on command. You can do it only once, but there is no restart possibility. So, that makes it not so useful. But for example, if you have a hybrid motor instead of a solid motor, you might have a slightly more complex system, but you could have start, shut off, restart, all that possible. Okay. It also means a phenomenal saving in terms of weight and volume. Okay. We will stop here. In the next class we will discuss about the turbo pump fed system. Thank you.